Okay, guys, welcome back. Last time we went over the basic unit of matter and how they were grouped in elements, right? We talked about carbon and oxygen and hydrogen and how these atoms were constructed. We also talked about bonding between these atoms. We talked about the fact that you could have bonds that where electrons were totally lost or gained, ionic bonds, right? We talked about covalent bonds, whether they're equal sharing or whether they were an unequal sharing of atoms. You may recall that we talked about, for example, an oxygen atom, so O2, right? These would have an equal sharing. Two oxygen atoms are not going to pull the electrons one way or the other any more than the other. And when these two atoms come together, actually, we would call this a molecule. Okay? Now, they're the same two atoms, so a molecule would be a perfect name for that tandem, those two oxygens together. But we also talked about the fact that you could have two hydrogen atoms forming polar covalent bonds with an oxygen atom, right? Now, this is also a molecule because it's more than one atom coming together, but this could also be referred to as a compound, right? So, two equal similar atoms coming together, it's a molecule. If you have more than one kind of atom coming together, it's a molecule, but we could also call it a compound. Now, these are all really small molecules that we talked about, but as we get into the human system and talk about the biological systems that are going on, we can see that certain chemistry is involved with the biological system, right? So whether we're talking about oxygen or water or anything else in the body, we basically are talking about biochemistry, right? The basic definition would be the study of all the chemical composition and reactions occurring in a living system, in living matter, right? But the fact is that what we need to do is break these compounds, these different molecules and compounds down so we can understand the composition of these different molecules and what they do for us, okay? So when we talk about water, for example, well, water, we already discussed, it had hydrogen and oxygen in it. There is no carbon in a water molecule, right? We even talked about sodium chloride. So we had sodium, right, Na, and it formed an ionic bond, right? And we will see sodium and chloride as ions in the human system. This is called a salt, okay? When these sodium and chloride ions get together, a cation and an anion, that's a salt, right? These are all small molecules, and we would say they are inorganic compounds because they have no carbon in them. That is the key, right? So when we're talking about an inorganic compound, it has to have the lack of carbon. Now, there's always exceptions to these rules. Generally, organic compounds do contain carbon. The only exception to this rule would be carbon dioxide, okay? Carbon dioxide has a carbon in it, dioxide, so there's two oxygens. But this is an exception to the rule. Carbon dioxide is a member of the inorganic group, okay? But as an organic life form, as we're considered an organic life form, we're talking about an organism that has lots of molecules with carbon in it, okay? So we have a biochemistry with inorganic compounds mixed with organic compounds, okay? Generally, organic compounds have a carbon atom in them with only one exception, and that would be CO2, carbon dioxide, all right? All right, so let's take a look at a simple inorganic compound like sodium chloride, right? We talked about sodium chloride as being like our table salt, right? and these form a rather strong bond. One electron being stolen by chloride and one electron being lost by the sodium, right? And they form table salt, right? Those crystals in your salt shaker. But let's consider what occurs when a salt is thrown into the mix in the human body, right? We have to remember that we make an aqueous environment for ourselves, a water environment for ourselves. So we are mostly water. And what happens when you throw a salt crystal into water? Well, remember, we go down to the bottom corner here. We have oxygen and 2 hydrogen atoms, and these come together to form this water molecule, okay, with charge involved. We have a negative charge on the oxygen, and we have positive charges on the other side of the water molecule where the hydrogens are. And we also have charge associated with the 2 ions, the cation in sodium and the anion in chloride. And these 2 ions are going to be completely distracted by water, right? If we prepare water for maybe cooking your pasta at home, okay, we want a little bit of flavor in there, we'll throw some salt into the water before we warm it up. And before you know it, that salt practically disappears, right? What is happening, in fact, is that the cations, the sodium, the cations, remember cat, the T has a plus sign in it, so we remember that, and the anions are completely distracted, and this salt crystal gets completely torn apart because these sodium positive particles are attracted to the negative oxygen atoms of the water, right? And so the salt will dissociate. We can say it's going to dissociate into its component ions when it's put in water. And that's why it looks like it disappears, okay? Sometimes you'll say dissolve too, right? When salt dissolves in water. And absolutely, this very same thing goes on inside of us because we're a water environment, okay? Now, what we could say then about these cations and anions is that they are hydrophilic. They are a hydrophile, sometimes you might say. Hydrophilic means that it's water for hydro, and philic or phile would mean loving, right? So it's a water-loving particle. Anything that has charge is going to have a tendency to dissociate and be attracted to those charges that water provides, okay? We could also say that the water itself exists as a solvent, okay? So in this situation, if we were to shake a few salt crystals into water, the solvent would be water, okay? The solute would be that solid crystal that we put in the water, okay? The solute would be the substance that is dissociating into the environment of the solvent. And voila, before you know it, a solute dissolved into a solvent gives us what we call a solution, okay? A mixture of solutes dissolved in a solvent, okay? All right, now, let's consider a salt that has one very special cation, okay? Again, let's consider the salt we've been talking about a lot so far, and that is sodium. So here's our Na sodium chloride. So in this case, we've had a positively charged ion associated with a negatively charged ion. Sodium was our positively charged ion, our cation, right? Now let's consider a very special cation in the form of a hydrogen atom. Now we know hydrogen atoms shared electrons when it came to the water molecule. In this case, consider a chloride ion that will have stolen an electron, just like it did when it interacts with sodium, right? It's this It's this bigger nucleus, 17 protons pulling for those electrons, and it can pull an electron away, making it an anion. Well, in this situation, when hydrogen interacts with chloride, we're going to have the hydrogen losing even more so. It doesn't just lose to oxygen like it did when it was sharing, right? At least it got a little bit of a sharing out of that. In this case, hydrogen is the cation, and we have an ionic bond. So in this case, if we think about salts that contain hydrogen as the cation, we call it an acid, okay? Well, so an acid is really nothing more than a salt, isn't it? So here we have a salt and hydrogen, hydrochloric acid is what they'd call it, right? HCl. And when we throw hydrochloric acid into water, it would dissociate just like salt would, okay? And it would increase the quantity of hydrogen ions in that solution. So by definition, an acid releases hydrogen ions and increases the concentration of hydrogen ions in solution, okay? Now, bases, by contrast, they would bind up hydrogen ions, okay? So they would actually not release hydrogen ions, but they would take them up. They would remove hydrogen ions from the solution, and they would decrease the concentration of hydrogen ions in solution. Okay? So we've got acids releasing hydrogen, increasing hydrogen ion concentration in solutions. Bases will bind and grab onto those hydrogen ions, effectively reducing their free movement in a solution. Okay? So these are two basic definitions for an acid or a base. Acids will increase hydrogen ion concentration in solution. Bases will decrease hydrogen ion concentrations in a solution. Okay? All right. So how are we going to measure the strength of an acid or a base? We'd have to be measuring the concentration of hydrogen ions in these solutions, right? So let's take a measure that we call pH. This is the measure of the amount of hydrogen ions in solution. This is a measure of how basic, if there's fewer hydrogen ions, or acidic, if there's more hydrogen ions, a solution may be, okay? Now, the actual measurement here is actually, I mean, if you care, I'm going to say it's the negative log 10 of the hydrogen ion concentration. It is an equation where you can actually measure it and get a number, okay? Now, I'm going to not ever have you really do that in this course, but I do want you to know that what the definition of pH is, the measure of the amount of hydrogen ions in solution, okay? Now, this is the tricky part, okay? It's a little misleading. Let's start with neutral. A neutral solution, we're not talking about atoms now, right? A neutral atom wouldn't have charge versus an ion that would, right? Now we're not talking about a neutral atom. We're talking about a solution being neutral. So what we could do is take a measure of hydrogen ions in solution, this long equation I mentioned, right? Negative log 10. You're not going to have to do it, but you would have to know that a neutral solution would be a pH measure of 7 if we were to measure a solution's number of hydrogen ions in solution. So take an example of what a neutral solution would be. Distilled water. Distilled water is going to be a pH of 7. We're going to have kind of a medium number of hydrogen ions. It's not basic, it's not acidic, okay? So if I were to say a solution's pH is 7, we know that it's a neutral solution, okay? Now, if I were to add an acid, like hydrochloric acid, to water and had it dissociate like a salt, okay, you would find that the hydrogen ion concentration would go up. It would donate hydrogen ions to that solution. And the trick about this is that we would say that it would become more acidic, but the pH value at that point would actually be a lower number. Okay? So when something increases in hydrogen ions, donates hydrogen ions to the solution, it will have a lower pH. So as we go below 7, so let's check this out, this scale here. We've got coffee, pH of 5. Okay, let's take, I've got this right here. I've got some soda here, not very good for you. Part of the reason it's not real good for you is because it's acidic. It does a job on your teeth. Acids can do a real job on bones and teeth, and we'll talk about that later. But a geek that I am, I brought those pH strips you get in chemistry. I brought that home, and there's a pH of 3 when I measured my soda when I got home. Okay, so that's not on our list here, but it was right in the 3 range. Okay, so this is definitely acidic. Some of your fruit juices, lemon juice, orange juice, definitely gastric juices. Gastric juices are real acidic. Okay, so an acid will have more hydrogen ions but a lower pH value. Okay, it'll be more acidic but a lower pH value. All right, if we go the flip side, we talk about solutions that contain less hydrogen ions. So we might think about molecules that bind up those hydrogens, take them out of solution. We would say that this is more basic. Let's change the color here. What are we using? We'll go with blue for basic. How's that? So we're going to have a lower number of hydrogen ions in solution. If it binds them up and they're not floating around anymore, then there would be fewer. And the tricky part is that the more basic something is, the higher the pH it is. Okay? So there's less hydrogen ions, higher pH. Versus acids, more hydrogen ions, lower pH. Okay? So as the pH goes up, we're going to have a more basic solution, less hydrogen ions, and a higher pH. Some examples. So household bleach would be a good example. Ammonia for cleaning, right? Oven cleaners, another good example of a really basic solution. All right. One thing I want to address also is that a really strong acid, let's say we're looking at something that's really strong and acidic out in this category up here, like sulfuric acid. Well, that'll burn your skin for sure because it's really acidic. We can have the same effect way down here in the basic category. If you get oven cleaner on your hands, that'll burn you too, okay? Because it's too acidic, it'll burn you. If it's too basic, it will burn you. These hydrogen ions and their quantity make a big difference when it comes to the biological system, okay? Okay, finally, we can't have the pH in our body changing drastically with time, okay? We talked about the fact that homeostasis must be something that we maintain, and we want to maintain that on all sorts of molecules that are dissolved in our system, right? We don't want too much or too little glucose. We learned about negative feedback there, right? We don't want too many or too few red blood cells. We don't want too many or too few sodium ions. You can take any ion you want to pick. We can't have these things going out of control. The same is true for hydrogen ions, H+ ions. We can't have these hydrogen ions too plentiful with an acidic situation, low pH, and we can't have it too few either. We can't have a basic solution, okay, with a higher pH. So what we have in our blood actually are molecules that are known as buffers, okay? Now what a buffer does is it kind of plays the role of both an acid and a base. We learned that acids donate hydrogen ions, add hydrogen ions to solution, right? More acidic, but the pH goes down. We learned that bases, well, they decrease the hydrogen ions in solution. They make the pH go up. But we need control over these. We need negative feedback control over these. And to do this, our body, for one, uses a molecule in the blood, and this molecule actually is found in the whites of fried eggs. Okay, so if you take the whites of your fried eggs and you look at the proteins that are found in those whites, you'd find that there's this protein called albumin. Okay, albumin is a buffer, and it's the most plentiful protein in our bloodstream. Okay, what albumin is capable of doing is albumin will bind to hydrogen ions when they are too plentiful. They'll act like a base, right? They'll take these hydrogens out of the blood and hold on tight. And if need be, if there's not enough hydrogen ions in solution, they will release and donate those hydrogens back into the solution. These albumin molecules are playing the role of a base, grabbing onto hydrogens so they can't be floating around free. So it acts like a base, and they'll release those hydrogens into solution and act like an acid when they need to. This will make sure that the pH of our blood never goes, we have blood here, right, in our scale. Blood is pretty close to neutral. A little bit basic, 7.4, right, a little higher than 7. But there is definitely a range, and we don't want to go too high with that range or too low with that range when it comes to our blood, okay? So again, we have this negative feedback control. In this case, a buffer is helping to maintain a certain range of hydrogen ions in solution and curbing that pH so it doesn't go out of control, right? Okay, I think that's enough for this particular clip. Next time we'll dive into some really large compounds containing more than one atom of different elements, okay? But much bigger than some of these acids and bases and salts we're talking about.